What's up, everybody? This is Mr. O'Brien. A few things before we start the lecture here that you'll see throughout the entire lecture series. The title, the atomic structure and size, is the title of the subsection of the unit. At the end of the subsection of the unit, you're going to get quizzed. In this case, the title is atomic structure and size. Every slide identifies where in the textbook you might find extra information so that you want to go back and read to. The slides themselves contain important terms that you'll see, and they'll also have questions on the slide to guide us through our little series. And then occasionally I'll pause to give you some points to check for understanding, to kind of reflect about what you just learned about. So let's go ahead and get started, yeah? So first question we'll start off is, what does matter? So matter is the stuff that makes up what you can and cannot see. So what you can, the macro scale, versus what you can't see, the micro scale. So the macro scale would be like the bench, the trees, the water. You can see all these things, so you know it's there, it exists, right? But what about the stuff that you can't see? How small does the matter go? For instance, in this bird, right, it's probably in that tree, you can't see where the heart's at, or where the kidneys are at, or where the lungs are at, based on what you see. Or even the clouds themselves. You can't quite see the smaller pieces that make up the clouds. So matter is visible at different scales, right? So where does that scale end? So we first have to characterize what matter actually is, right? And so there's two characteristics of matter. First, that it takes up space, and then it contains mass. So imagine the picture here of the produce and the vegetables. You see that you have broccoli, you'll have like maybe an onion, maybe some lemons, potatoes, carrots, and they're all different sizes. But yet, based on the size, it doesn't necessarily mean that it weigh heavier or lighter, right? Each of these objects have different amount of mass inside of them, different amount of stuff, right? And so matter really is how much space these objects take up and how much mass it contains, right? So here's your first checking for understandings. I want you to reflect about what you just learned about and think about this question. You can't always feel air, nor could you see it. However, if given a balloon, how would you prove that air is matter? Because it is. So how does matter then relate to chemistry? So in chemistry, we attempt to explain at the microscopic event that leads up to the macroscopic observation that we see. So in solid, it's a solid object that really doesn't move much, right? Or it's got a set shape. But in liquid, as you melt the solid, it kind of swirls around a little bit, right? And then when you evaporate that liquid, add more heat to it, it kind of fills up the whole container. So what happens to the matter that allows us to see these observations? That's what we try to hit up in chemistry. I'll pause for a second here. Can you correctly identify where in figure A would you see the macroscopic observations? Where's the microscopic events identified here in this picture? So let's start with another question. So what were the earliest ideas of matter? So the Greeks essentially were the first to try to attempt to explain what matter was. And they did this through thinking. There's no scientific experiments. There's no, instrumentation. They just thought about what matter was, like what you're trying to do here. You see this gas. You see that it takes up space. So what is allowing it to take up space? Philosophers once believed that matter, these objects here, were really composed of just four things. We have earth, water, fire, and air. But nowadays, 2,000 years later, we have a periodic table that identifies more than four basic elements. So what were the earliest ideas of matter? Continued on with philosopher Democritus, which he kind of thought about and envisioned that matter wasn't completely divisible. There's some sort of point that you can't break up matter anymore. And what he identified that is atoms, right? And that the matter, even though that you can see it, consists of empty space in which these atoms can go through. So if this idea of atoms came up 2,000 years ago, why don't we have more on that now? The problem was about 2,000 years ago, there's other more influential philosophers like Aristotle, who believed in that nothingness was impossible. There's always got to be something. So because really Democritus didn't have any proof, right? And he just thought about and didn't have any experimentation, there's no way to persuade others, right? Think about this for a moment, right? Have you ever felt like Democritus? Do you ever believe in something and knew it was right, but was challenged on how to persuade somebody? So how did the idea of atomos change 2,000 years later? Well, we have advancements in science now. We have advancements in instruments, right? In experimentation and data collection. In 1803, John Dalton was really the first that used experimentation on gases and noticed that atoms of different elements are unique. And they can combine with other atoms in simple whole number ratios to form molecules. Here's a picture of John Dalton's first idea, a list of 20 elements of atoms. And each of these atoms, you can see, they have like different colors associated, different designs to differentiate them. And John Dalton thought that, hey, man, you can combine these to get new matter, right, into different ways. But it's important to know that the atoms of the same element are essentially the same mass. They look almost identical. And so the elements of different matter, say like oxygen versus hydrogen, which they're different, right? They're going to have different masses. So their atoms are going to be slightly different. But you can combine these, which John Dalton stated, into specific ratios to get certain combinations. Like consider like carbon dioxide, like carbon and 2 oxygen molecules, or carbon monoxide, right? So you can combine them in certain ratios, right? So what exactly is an atom? So an atom is an extremely small piece of matter, roughly the size of 10 to the minus 10 meters. So think about an average human being, right? And about an average human being, the size of matter would be 10 billion times smaller. There's more to it than that, but that's essentially how small an atom is, right? We can combine these atoms, rearrange them with other different atoms to make new matter, right? So an example here, atoms of element A with atoms of element B, if you hook these up together in a chemical reaction, you can get a new substance, new molecule, new matter, right, in a specific ratio. And then the atoms can be divisible into smaller parts, even things we call subatomic particles. I'm going to pause for a second. I want you to think about what you just learned here, right? And think about this question. So like a water molecule, H2O, here on the right-hand side, has 2 hydrogen atoms and an oxygen atom. An atom of hydrogen has a mass of 1 AMU, essentially like a pound. An AMU is like the size of mass at atomic scale, super small. And an oxygen atom has a mass of 16 AMUs. So if hydrogen and oxygen could combine to form water, H2O, could a molecule have a mass of 9 AMU? Does that make sense? If it doesn't make sense, think about why not.